Hello, and welcome back to the channel. Today, our focus shifts to a fundamental concept in building high-performance, scalable systems: caching. Often referred to as the speed hack, caching is absolutely critical for optimizing performance and ensuring responsiveness in modern applications. Fundamentally, caching involves storing frequently accessed data in a temporary, high-speed storage layer. Think of it as the short-term memory for your entire system, sitting much closer to the user or application than the primary data source. The core purpose of caching is to dramatically reduce latency by serving data directly from this fast layer, rather than repeatedly fetching it from slower, more distant sources like a database or an external API. This not only significantly improves system speed, but also substantially decreases the load on your backend databases and application servers. Caching is a ubiquitous optimization technique, implemented across virtually all layers of the internet, from the user's browser through content delivery networks, CDNs, within application servers, and even at the database level. It truly is a vital cheat code for achieving optimal performance in complex, distributed systems. The rationale behind caching is compelling and multifaceted. Firstly, in virtually any popular application, users frequently request the same data repeatedly. Consider a popular news article or a product listing. Fetching this identical data from the primary database for every single request is incredibly inefficient. Secondly, and perhaps most importantly, there's an immense speed disparity between different storage mediums. Reading data directly from an in-memory cache is often literally hundreds of times faster than executing a complex query against a persistent disk-based database. Thirdly, caching provides a crucial buffer, allowing systems to gracefully handle sudden spikes in traffic. Instead of overwhelming the database, many requests can be served directly from the cache. Lastly, by reducing the load on your primary data sources and backend servers, caching often leads to significant reductions in infrastructure cost, as you can serve more users with fewer or less powerful compute resources. A prime example is an Instagram feed. The same feed data is heavily cached and served to millions of users, dramatically reducing the load on their core data stores. The types of data suitable for caching are diverse and depend on their volatility and access patterns. Static data. This is perhaps the most straightforward category. Think of assets like images, CSS files, JavaScript bundles, or even relatively stable product listings that don't change often. These are ideal for long-term caching. Dynamic data. While seemingly contradictory, even dynamic data can be cached, especially if it changes less frequently than it's read. Examples include authenticated user profile information, general pricing structures, or aggregate dashboard statistics that might be refreshed every few minutes rather than every second. Query results. The results of frequently executed database queries with predictable patterns are excellent candidates. Caching these results avoids repeated, expensive database lookups. API responses. If your application relies on external services for data, e.g., a weather API, stock quotes, or currency exchange rates, caching their responses can significantly reduce your dependency on external network calls and improve response times. Rendered pages. For server-side rendered applications, entire rendered HTML pages, e.g., a static product detail page, can be cached, allowing the server to serve a pre-computed response without re-rendering for every request. Caching occurs at various layers of the system architecture, each serving a specific purpose. In memory cache, this is the fastest type, residing directly on the application server's RAM or on dedicated caching servers, like Redis or Memcached. It's used for frequently accessed application data that needs ultra-low latency. CDN cache, content delivery network CDNs like Cloudflare or Akamai cache static assets, images, videos, CSS, at edge locations, geographically closer to the end users. This drastically reduces latency for content delivery and offloads traffic from your origin servers. Database cache. Many modern databases incorporate internal caching mechanisms at the query level to avoid re-executing expensive, repetitive queries, or at the row/block level. Browser cache. Client-side cache. This is stored directly on the user's web browser. It's limited in control by the server, but is highly effective for individual user experience, as the browser can retrieve static assets without making a network request. Reverse proxy cache. A reverse proxy server, such as Varnish or Jinx configured as a proxy, sits between the client and your backend application servers. It can cache entire HTTP responses, serving them directly, without involving the application server for subsequent requests. How you interact with the cache and the primary data store defines your caching strategy. Write-through. In this synchronous approach, data is written simultaneously to both the cache and the database. This ensures data consistency, but can introduce latency as the operation waits for both writes to complete. Right behind, right back here, data is written to the cache first, and the write to the database occurs asynchronously later. This offers faster write performance, but carries a small risk of data loss if the cache fails before the data is persisted to the database. Cache aside, lazy loading. This is a very common strategy. The application first checks if the data is in the cache. If it's a cache hit, the data is returned immediately. If it's a cache miss, the application fetches the data from the database, stores it in the cache, and then returns it to the user. This is simple, but can lead to initial latency on cache misses. Read-through. In this strategy, the application never directly touches the database for reads. Instead, all read requests go to the cache. If the cache doesn't have the data, it's responsible for fetching it from the database and populating itself before returning the data. Eviction policies. Beyond strategies, you need policies for when to remove data from the cache. Common ones include LRU, least recently used, which removes the oldest accessed item, LFU, least frequently used, which removes the least frequently accessed item, and TTL, time to live, where items expire after a set duration, regardless of access. While caching offers immense benefits, managing it effectively introduces what's famously known as the hardest problem in computer science, cache invalidation. This refers to the challenge of determining precisely when cache data is no longer valid because the underlying source data has changed. If not handled correctly, serving stale or incorrect data from the cache can lead to serious issues, from incorrect pricing to misinformed user decisions. Common techniques to tackle this include time-based expiry, TTL, setting a time to live on cached items, after which they are automatically removed, ensuring eventual consistency. Manual purge on updates. When source data is updated, proactively sending a signal to the cache to invalidate or purge the corresponding cached entry. Versioning the cache keys, including a version number or timestamp in the cache key itself, so that when the underlying data changes, a new key is generated, effectively invalidating the old cached entry. Effective invalidation is crucial for maintaining data freshness and system integrity. Familiarity with standard caching tools is essential for implementation. Redis, an extremely popular open source in-memory data store. It's ultra-fast and incredibly versatile, supporting various data structures, as well as features like time to live, TTL, for expiry and publish-subscribe, pub/sub messaging. It's widely used for caching, session management, and real-time analytics. Memcached, another open-source, high-performance distributed memory caching system. It's generally simpler than Redis, focusing primarily on key-value storage for caching. It's often favored for its multi-threaded architecture and ease of deployment for simple caching needs. Cloudflare. Beyond its CDN capabilities, Cloudflare acts as a powerful global edge cache. It caches static content at its numerous data centers worldwide, dramatically speeding up content delivery to users based on their geographical location and significantly reducing the load on your origin servers. Varnish Cache, an open-source reverse proxy HTTP accelerator specifically designed to cache HTTP responses. It sits in front of your web servers, significantly speeding up content delivery for subsequent requests by serving cached responses directly. These tools represent industry standards for implementing various caching strategies. Let's apply caching to a tangible example, an e-commerce platform. The homepage, which might display trending items or static promotional banners, is an excellent candidate for aggressive caching. Its content changes infrequently relative to its access frequency, so it can be cached for a relatively long duration. Product detail pages, which are semi-dynamic, e.g., prices or stock might update occasionally, can be cached with a short TTL, time to live. This balances performance with data freshness. Conversely, sensitive, highly user-specific and real-time components like the shopping cart or the checkout process should generally not be cached. Caching here could lead to incorrect order totals, outdated item availability, or security vulnerabilities if personalized data is accidentally served to the wrong user. Implementing smart caching throughout an e-commerce platform leads to a significantly faster user experience and substantial reductions in infrastructure cost as fewer requests hit the expensive back-end database. Just as important as knowing what to cache is understanding what not to cache. Misplaced caching can lead to severe issues. Frequently changing data. Anything that updates very rapidly, such as real-time stock levels, live sports scores, or dynamic financial market data, should generally not be cached, or only for extremely short durations, as serving stale information would be detrimental. Highly user-specific secure information, critical, personalized data like a user's bank balance, personal health records, or current order status in a financial or healthcare application should never be cached in a shared cache due to privacy and security implications. Anything that must always reflect real-time state. If your application's logic or user decisions absolutely depend on the immediate, precise current state of data, then caching is inappropriate. Bad caching can lead to incredibly problematic outcomes, such as displaying the wrong price for a product, showing an outdated inventory, or presenting incorrect account balances, which can erode user trust and cause business issues. To test your understanding, let's consider a quick quiz. Guess what's cached? We'll show you 4 items, and I'd like you to consider which ones are likely cached and which should absolutely never be. First, a trending YouTube video feed. Second, a real-time sports score. Third, product search results. And finally, a user password reset token. Think about the characteristics of each, its dynamism, its sensitivity, and its reusability, which are good candidates for caching and which demand real-time fetching. Answer in the comment section. To conclude, caching is not merely an optimization. It is a core pillar of modern system performance and scalability. It's the mechanism that allows applications to handle massive loads and deliver lightning-fast experiences. For your future endeavors in system design, remember these key takeaways. Understand what, where, and when to cache. Carefully analyze your data's volatility and access patterns. Master common strategies. Be proficient in approaches like cache aside, write through, and understanding eviction policies like TTL or LRU. Familiarize yourself with industry-standard tools. Tools like Redis, Cloudflare, and Memcached are indispensable for implementing effective caching solutions. Crucially, always be aware that bad caching can lead to severe issues, ranging from serving stale or incorrect data to creating potential security vulnerabilities. Proper cache invalidation is paramount for maintaining data integrity and user trust. Before you go, I'd love to hear from you in the comments. If you found this video helpful, do give it a like, share it with your friends, and of course don't forget to subscribe to the channel to help us grow. I will see you in the next one. Till then, happy learning.